We'll proceed in the curl in calculus. Curl, one of the toughest thing in calculus. I mean, someone has to crack the curling. You would have seen cracking some examination or cracking some kind of programming. So, cracking a curl is a kind of aspect that is that is required. Cracking curl. Cracking curl. Okay, so what is curl and what we have seen till now? What is curl and what we have seen till now? So curling is nothing but if I have a vector field we have talked that vector is static. 3i plus 2j plus 4k is a static vector in the sense that vector has components. So all the components are static and it is a static vector. It is a static vector. If it is a static vector, then what about vector equation in xi plus xj plus y plus zk? Then its components are algebra. If a vector which component is algebra, it is also called vector field. Algebraic vector is also called vector field, or a vector field is a vector which produces many vectors. It's a function which produces many functions. Algebra is also called a function which produces many values dependent upon the independent variable. If that is the case, then if I have a vector field f, capital F, equal to algebraic equation I plus algebraic equation j plus algebraic equation k, then it is considered as this vector is an algebraic equation which produces infinite static vectors depending upon the independent variable. Now case is that if I have a vector field, okay, so okay, so the case is if I have a vector field, consider that this is x-axis. This is x-axis and and this is a vector that is 2i. If it is 2i, then it is 2i, 2i, 2i. Everywhere it is 2i. I am not talking about parametric vector, simple vector. Or this vector equation is xi. Vector equation is xi in I direction, but the strength of the vector is dependent upon the x. Now it becomes a vector field. If vector is 2i, if vector is 2i, then it is static vector. But if it is xi, then it is a vector field. But its direction is only in I direction. Now all along it is xi. So all along if I take this much, then it becomes a vector field. Vector field in a sense that this is the vector field where vector goes from left to right. Oh, so this is xi, this is xi, this is xi, this is xi. It forms a vector field like a magnetic field. Magnetic field is xi means its magnitude is x, which is variable upon x-axis, and I is the direction. This is north pole, this is south pole. This is the magnetic field. Pull in I direction, magnetic field is going. Like this is a vector field. If I keep any item here, it will be pushed like this in the vector field. If this is the vector field, consider the river is flowing, vector field is xi. If you keep any item here, then item will move on because river water that is xi, consider it is a force. Xi is a force, then it is doing some work. What is tendency of xi to make this item rotate? That is curling. Can it rotate the item or it will just push it through? Like if I drop a paper, small paper on the river, and if it starts rotating, this means that the force, that force vector that is in the river, that is doing circular work. It has tendency to rotate something. So that is something different in the kind of in a vector field, that is curling. What is tendency of a vector field to make any object rotate? So that is curling. Okay. Now then we move ahead and we started seeing talking about path independence. Path independence is if I have a vector field capital F, that is a force, then what is the work done by the force? Okay, then work done by the force along which direction? That is the concept. Along r direction. Then F vector dot d r vector along x-axis. If force is like this, if force is like this, then how much it does the work along x-axis? Zero, because whatever item it has, it will push in this direction. That is what I don't want. I want item to be pushed in this direction, but it will push everything in this direction. So if this direction is r vector, then F dot product dr vector. Actually, the work done is force into displacement. F into r vector. F vector dot r vector. But it is calculus, d will come in between. So please watch all the video. So F vector dot d dot dr vector. Now if it is x-axis and this is y-axis, then there is no work done along the x-axis. But if f is like this, then certainly some work done is along x-axis, some work is done along y-axis. I am interested in x-axis. So part of this force that is along x-axis, that will come into the picture when we want to see the forces displacement along x-axis. If that is the case, then it is F dot dr, F dot dx vector. If F is completely along x-axis, then it is F dot dx, where F is like xi, then x dx. That is the work done along the x-axis. But if F is xi plus yj, it has j component also, then net magnitude of the force is x square plus y square square root. But we are interested in x-axis component, then yj will go away. So now the force that will come along the x-axis is xi only. Yj will not come into the picture. The power of the force that is along x-axis is x only. So earlier it was x square plus y square square root. Now it is only x. So power of the force along x-axis is reduced. So this is normal work done, fundamental work done is force vector dot displacement vector. It is calculus. So F dot d r vector. This is what we saw. Now if I want this work done along, if this is r vector, this is force vector and this is any r vector. This is force vector, this is any r vector, and this is x-axis. This is x-axis, this is force vector, and this is any r vector. If that is the, this is force vector, this is any r vector, this is x-axis. If that is the case, then work done by force vector is f vector dot dr vector. Okay, so that is the concept. From a position here is a and position here is b. From a to b, the limit is from a to b. F vector dot dr vector, limit is from a to b. Okay, so that is the concept. Now it is path independent. I am saying it is path independent. Path independent means if I am doing the work done along any vector r from point A to B. Now point A to B is a straight line. Point A to B is a straight line, not required. Okay, it can be a point A and B. Just keep the point A and B. Now between A and B, it can be a straight line, it can be a circular arc, it can be parabolic arc, whatever it is. Okay, does our if our calculation matters when I am calculating f dot dr, where r vector is a straight line, r vector is a circular line, r vector is a parabolic line. Does it matter when I am trying to calculate the work done from point A to B, where point A and B, between that, the line I am talking about, r vector, is circular, parabolic, straight line? Does it matter, or it only matters between point A and point B, like earth gravitational pull? Okay, earth gravitational pull, there is a force that is pulling it. Okay, what is the work done by the force when it is from here and it is coming here? How much is work done? Work done is directly proportional to two endpoints, not how it comes. So if I make a stair, so what is the work done of okay, I am dropping something. I have a four-story building, and from the fourth floor to second floor I am dropping a ball. How much is work done by the gravitational pull? Or if that ball I just kind of pushed along the stair. From the stair, it is going down, down, down from fourth floor to second floor. Is there any difference from the work done by the gravitational pull? No. Gravitational pull, the work done by the gravitational pull is purely dependent upon the first position and second position, not the path. It can be a straight line, it can be a staircase, or someone can make a circular arc and then he drops the ball, it goes like this, doesn't matter. So whatever the work done, F force vector dot dr vector, capital F, on top of each arrow, force vector dot d, small d, then r vector, r on top of it vector, where r is the path. Limit a to b, from a to b. Okay, path independent means r, this full calculation is dependent only upon the force vector and end point a and b, not on the path. This is called path independence. Path independence. Or if I calculate a to a, this is what we were seeing. If I calculate the integration from a to a, then it should be 0. Certainly it will be 0. But if I say a to a means not a to a means a to b, b to c, c to d, and d to a, that is also a to a only. If I calculate integration a to b plus b to c plus c to d plus d to e plus e to a back, if I calculate all this, it is same as a to a. Okay, if it is full is coming 0, then this vector field is path independent, like the earth gravitational pull, that is also a vector field. And if I am calculating from a, if I am calculating from a to b, a to a means if I drop a ball from a to b and then push the ball from b to a, net energy should be 0. Energy. So whatever the work done we are getting from the gravitational pull, it is also called energy. Work done. Work done is energy. This is called potential function. If I have capital F dot dr vector integration, if the leave the lower limit and higher limit, F vector field F dot dr vector field, if I do this, okay, then whatever comes as algebraic equation, consider it as small f or small g. Consider it is small f. Okay, if it is small f, capital F is vector field, where small f is the net work done. That is again an algebraic equation, and I set limit from a to b to get the net work done. If small f, that is also called potential function, potential energy, potential function. So if I have a force field, earth force field, if I have earth force field and point A to point B, how much is the work done by the earth force field? If I want to calculate that, how much is the work done by earth force field point A to point B, then F, capital F dot dr. But that will result in a small function that is called potential function, energy. So the force into displacement gives the work done or energy. But if it is not dependent upon the path, then potential function, whatever it comes, it is not dependent upon r. R can be a straight line, it can be a circular, it can be parabolic. Only thing matters is point A and point B. If that is the case, then energy what we are getting, it is completely dependent upon the force vector field and limit A to B. This is what I am trying to say. If I know gravitational pull how much it is, and I know point A and point B, what is the work done? If it is completely, the calculation is completely based upon the force vector field and point A and point B, not dependent upon the path, either it is a straight line, circular, then this force field, vector field, or this vector field is called path independent. It is path independent. Either you drop ball from A to B, what is the work done by the force vector field, or you make a arc, and inside pipe you keep the ball will rotate like this. Then what is the work done by the force field from A to B? Make a parabolic, whatever, work done will be same. So work done will be same means work done, that is the potential function. So this move proves that at point A there is a potential energy, point B there is a potential energy. What is the difference of this potential energy is the work done. If I have F dot dr results in a small f, then small f I have to set limit A to B, that is f, small f, the small f. If I have capital vector F, vector field is capital vector F. Capital vector F dot dr is the path. If I do integration and it results in small f, that is algebraic equation, and this integration is from A to B, then small f, that is considered that is fr, fxy. Small f is fxy. Then fxy I have to set from lower limit, that is A to B. That is nothing but fb minus fa. If F is the potential energy, this is what we are talking. If F is potential energy, then what is the potential energy at point B? A to B, A to B. What is the potential energy that is at point B? What is the potential energy at point A? You just subtract it and you get the net work done. If that is true and it is path independent, then this potential function, small f, potential function is only dependent upon capital vector F, vector field, and limit A and B, not on the R. This is called path independent. If this is path independent, then from A to A, the integration is 0. This is what we talk. You take any path, A to B, B to C, C to D, E to F, F to G, and back G to A. Like if I have a potential, if I have a vector field, equation is xi. Equation is xi. If vector field equation is xi, if vector field equation is, this is x-axis. If vector field equation is xi, then this is x-axis. This is the vector field. What is the vector field from the line integral is from A to A, means A to B and B to A. It is 0 because A to B, whatever I calculate, B to A in the same path, it will be reversed and it will be 0. Consider it is x plus y I. This is what we are talking. The force vector field is x plus y I. X plus y I along x axis. So x plus y I dx vector. X plus y I dx vector. Leave it. Now, what is the force field along x axis? That is y equal to 0. So it is xi only. What is the force field when y equal to 10? Then force equation is x plus 10I, because y is constant along the x axis. So force is along I. So whatever work done is with xi into some distance from point A to B, whatever is work done with x plus 10i from point A to B will be different, because that is x plus 10i. X plus 10i from A to B is different than xi A to B. If that is the case, then if I draw a vertical line, this is point A and this is point B. Earlier we taken A and B here. Consider A, this is point is C. A to C, what is the line integral f dot dr? So f dot dr means r is y-axis, f dot dy. But f is only along I-axis, so no work done, orthogonal. What is work done from point C to D? Vector. So vector is now x plus yi and this height is 10. So x plus 10i. X plus 10i dx. Whatever it is. Now from D point to a point B, this is my original point B. So D to B, what is? Again 0. From B to A back, then again that is force is xi, but it is B to A. Okay, so if I calculate this, then whatever this was 0, this was 0, this was x plus 10i dx from A to B, and this is xi because y is 0, x plus yi is the force field. B to A, it should be exactly same as what we calculated, negative. Then the net A to C, C to D, D to B, B to A will be 0. But it is not 0 because this one is bigger and this one is small. So it will turn up into some positive value. So the vector field line integral from A to A is not 0. It is not 0. If that is the case, then this vector field is not path independent, because depends upon the path, right? If it is A to B and B to A in a straight line, it is 0. But if it is like this, where vector field is x plus yi, it is not 0. So if I take any path from A to B, I had taken one rectangular path, I take a straight line path, or I can take a circular path, circular path A to B, okay, or parabolic path from A to B. If I keep taking these paths, then everywhere it should be 0. How many paths you will take? I am telling you, prove that this vector field is path independent. Path independent in the sense, if I do line integral vector field with dot dr from A to B, R is straight line, R is a circular line, R is a parabolic line, whatever it is, the value should come same from A to B or A to A. If I take different path, calculate A to E should be okay. Then for all possible R, it is staircase, it is para how many? Now prove it. Now you try 4, 5, 6, 7, 8, 9, 10 path. Then you said it is path independent. I went for 12 path where path it was not path independent. How to prove that my vector field is path independent? So the biggest proof is if you calculate in line integral from A to A through calculus, because calculus will do full integration. If this is a vector field, if this is a path and this is a vector field, if I do line integral, then it's algebra, right? Every moment it will do dot product and it will calculate line integral. That is the class of algebra. Every moment full path it will do line integral with f dot dr. So if line integral from A to A, that is also called closed loop line integral. Closed loop line integral. If I am able to calculate closed loop line integral f dot dr for all the paths possible, no need to take the kind of breaking the path. I am breaking the path. If it is rectangle, then this path plus this path plus this path. Just get the algebra and calculate the f dot dr from A to A. So in a closed loop, if A to A is 0, then for all possible paths, then it is it is this vector field is path independent, but for how many you will calculate through integration. No need to break into part. From A to A only you can calculate, or in a closed loop. It is also called closed loop. So in a closed loop you can calculate, but for how many shape you will calculate. What is the proof that we can consider that we will take to calculate the to prove it? This is the question, that if this vector field, a gravitational vector field, prove that gravitational vector field is path independent. That is the question. Prove that uh, the earth vector field is path independent. How many ways you can prove? That is the question. We will see many ways, and one way is our way. One way is our way. How to prove? Now question arises is, can we prove in a closed, can we just prove it that my vector field is path independent? Path independent means from A to A, means in a closed loop all possible path from A to A, from A to A. You take circular path, you take rectangular path, you take parabolic path, you take a staircase path, whatever. A to A should be 0. I'm not saying from A to B, then this value should be there. Just prove it A to A should be 0 for all possible paths. For all possible paths, it is not possible to calculate this. How we can be sure that our vector field is path independent? That is the question, and how many ways we can prove it, that is bigger question. Let's prove it. Okay, so that we will see step by step how many ways we can prove it. Okay, the first proof that we will propose, we will propose the first proof here is, let's, if it is path independent, let's take a generic path. Is it possible that for vector field line integral I can do through a generic path? This is our proof. Okay, you will not find anywhere in the book. Our proof through generic path. Otherwise, we have curling proof, we have Green's theorem, and we have normal proof also, and so many proofs. So everything one by one we will talk to prove that our vector field is path independent. Means work done through vector. If vector field is a force vector field, then line integral will result into work done. Okay. So if there is a vector field, if there is a vector field is like this, and this is the path from A to B, what is the vector? How much this vector? If I keep a mass here, and mass slowly it moves from point A to B because of this vector field's energy. If that is the case, then how much is the work done by this vector field moving a point mass from A to B? That is the vector field. If it is a force vector field, then F dot dr, where r is and from A to B. So that is line integral. Force into displacement. Displacement is A to B. Displacement is point A to B. Then this distance is covered, and this is force. Then force vector field dot dr. R is the circular. This from A to B. Integration is from A to B. If it is path independent, this point A and B, just remember it. If it is a straight line also, it is a parabolic line also, it is a staircase, goes up and goes down, but point A and B are same, then all result F dot dr, where R is different, the net A to B should be same. This is path independent. If that is the case, then A to A should be 0. Okay, so that we will prove.